Hey guys, welcome to the channel Learn Competitive Programming with CodeChef. So this channel brings to you a good quality content on data structures and algorithms, as well as CodeChef's contest video tutorials. If you are new to the channel, then please do subscribe to the channel and turn on the bell notification. Myself Chirayu Jain, I'm a CodeChef educator, and in this video series we are going to understand trees, and the topic for today's video is binary trees and its types. So let's get started. Okay guys, so now let us start the discussion on binary trees, right? So what are binary trees, right? So let's start off with the definition first. So what is a tree? A binary tree? A tree which has at max two children is called a binary tree, right? So we'll get into the terminologies. What is this children, right? What are child of a binary tree, right? So there are some terminologies associated with a tree, that is root, what is a parent, what is a child, leaf, siblings, height of a tree, right? So these are certain terminology. So let's step by step discuss each of the terminology, right? So first of all, the thing is root, right? This particular node, the starting of the tree from which a tree originates, right? It branches originate, a child originate, right? We get to the leaf node. This is the starting point of the tree. That is called a root node, right? So that is called a root. This is the first thing. What is a parent? Parent is obviously, right, there are some children, right? So the parents are the one who give birth to their children, right? So the originating nodes of the childs are called parents, right? So let's see, these are the childs 2 and 3. For which parent it is the child? Because one is the originating of these two, right? 2 and 3. So one is the parent of this 2 and 3. Right, so this is the important thing. Parent is the node which originates their child, right? This is the parent. Here 2 is the parent of 4. 2 is the parent of 4, right? So this is the terminology for parent. Obviously parents originate child, so we have gone through this definition of child, right? So the child is the nodes which are originating from the parent, right? So here 2 and 3 are childs of 1 and 4 is the child of 2. This is what leaf. What is a leaf? Leaf are the extreme endpoints of a tree. So we are just comparing this, all of the definitions with the original tree, right? So there is some similarity, that's why we have given the conventional name to this data structure as tree, right? So what is a leaf? Leaf are the extreme endpoints of the tree, right? So if we see here, this is a full tree, right? This is a tree. So 4 is a endpoint, last endpoint of this particular left subtree. If we see from the root, right, so we'll get to know what is this left subtree and all, but yeah, if you see, this is an extreme endpoint, that is a leaf. If you see here at the right hand side of this tree, so there's a 3 which is extreme endpoint, right? So we need to know what are the extreme endpoints of the tree, right? That is called a leaf node, after which there is no child nodes or no nodes for that particular branch, right? So that is known as the leaf. What are siblings? Siblings are at a particular level. So before knowing to siblings, we should know that what are levels, right? So this is certain level 0, level 1, level 2. If we are conventionally giving starting from the level 0, so this is level 0, level 1 and level 2. Particular level, how many nodes are there, right? So let us say at level 1 we have 2 nodes. These 2 nodes are considered as the sibling of each other, right? These 2 nodes are considered as sibling of each other. So that is a sibling. What is the height of a tree? So generally height refers to this height, right? So this is the height of a tree, right? So if we see, the height of the tree is 2, right? So we have 2 levels and that denotes the height of the tree, right? So these are certain terminologies which we need to know before just going into the depth of what are binary trees and some of the major things. Now we know that a tree which has at max 2 children, right? So it can have 1 and 0 as well, right? So at max 2 children is called a binary tree, right? For each parent there are at max 2 children, that is known as binary tree. Now these binary trees also have some classifications, right? The classifications are generally on the basis of the fashion of the nodes, right? So majorly we divide these into 3 categories, that is complete binary tree, full binary tree and perfect binary tree. So prominently we use complete binary trees, but we also should have the knowledge of full binary trees, what are these, and the perfect binary trees, right? So let's step by step discuss what are these and some of the technical things of these binary trees. So let's start. Okay guys, so now let's start the discussion on complete binary trees, right? So we have seen what is a binary tree. Now let us start with the first thing that is very important and very prominently used, that is complete binary tree. So let's start with the definition first. A tree in which all the levels of the tree are completely filled except the last level. So except the last level, all the levels are completely filled, and the last level is like maybe partially filled, right? And the filling is from the position left to right. That is very important, right? So we fill generally a binary tree, a complete binary tree will fill from left to right, right? So this is what the typical definition is. Let's see this particular example. So here we can see there are three levels: level 0, level 1, level 2. We can name it like that. And level 0 has the root node and then followed by some nodes, right? So if we see, this root node has two childs, that is 2 and 3, and then they have this child that is 4, 5 and 6. So this is the last level, right? We can observe that this last level is partially filled. We can have one more child here, but we don't have that, so it is partially filled, and this proves to be in the condition of the data structure complete binary tree, right? So this is a typical example of complete binary tree, right? So what conditions do we need to check? That all the levels are filled, completely filled, except the last level, which can be filled or not, right? And the filling of the nodes is from the left to right, right? It cannot be that we have certain nodes here and some of the nodes are missing here. The filling structure should be from left to right. So that is a definition of complete binary tree. This H denotes the height of the binary tree, right? Now there are certain things associated with that, right? So the first important thing is, what are the total number of nodes that can be in a complete binary tree? So this is a typical case, like this is the formula, like the total number of nodes in a complete binary tree is ranging from 2 to the power h, where h denotes the height of the tree, till 2 to the power h plus 1 minus 1, right? So this is the portion, right? So why this 2 to the power h? Because at each level, what we can observe, how many nodes are there? 2 to the power 0, only a single node. 2 to the power 1, 2 nodes, right? Here we can observe that it is less than 2 to the power 2. Ideally, if it is all filled, if there was one node here as well, so how many nodes were there? That is 4. That is equal to 2 to the power 2. But at the last level, we can have either all the nodes completed, that can be a part of perfect tree as well, but we have some incompletion in the last level, right? So it is generally less than this 2 to the power 2 or 2 to the power h for a certain height, right? To the power h we are taking, right, for a certain height. So but the question arises that we need not to calculate the total number of nodes at a level, right? We have to calculate the total number of nodes in the whole binary tree. So how we'll calculate it, right? So if you observe here that 2 to the power 0 plus 2 to the power 1 plus 2 to the power something, like not completely but something 2 to the power 2, this gives us something, a geometric series, right? A geometric series we have always learned in our schools. So this is a kind of geometric series, so we need to sum it, right? So what is the formula for it? So we have written here that 2 to the power 0 plus 2 to the power 1 till a certain height h. What will be the sum? That is equal to 2 to the power h plus 1 minus 1. So you can refer to the geometric series if you have certain doubts, then you can easily be able to resolve it, right? So this is the formula for it, 2 to the power h plus 1 minus 1. So by this formula we can show that at max, if this node was also there, we can have these much of nodes at max, right? So we have conquered the right max, that is till this level we can have the maximum nodes. Now what can be the minimum? What can be the minimum, right? So we know that this binary tree has a height of h. That means that is perfect, right? That means that is we are sure for that. The height we are sure for that, right? So what can be the number of nodes there? Because this is a height h, so we do have at least some of the nodes here, right? At least some of the nodes here of height that only defines that this binary tree has a height of h, right? So what we can say here, that this till this, right, till this position, how many nodes do we have, right? How many nodes do we have till this particular position, right? So till this position, how many nodes we have? So the height will be h minus 1 here, the height will be h minus 1 here, right? So let's sum it, 2 to the power 0 plus 2 to the power 1 till 2 to the power h minus 1. So what will be the sum here? That is 2 to the power h minus 1 plus 1 minus 1. This will be the sum. So minus 1 plus 1 becomes 0, 2 to the power h minus 1. So till this, how many nodes do we have? That is 2 to the power h minus 1. And since the height of the tree is of height h, right, since the height is of length h, so we at least have a single node at this particular level. That is the minimum bare requirement of this particular condition, that if a tree has height h, that means at this particular level we at least have a single node. So that means we have plus 1 over here for fulfilling this condition, right? So till this position we have 2 to the power h minus 1 nodes, and at this particular level we at least should have one node. So that means this minus 1 plus 1 get cancelled, and the bare minimum condition for the tree to have height h is 2 to the power h. That's why we have written this 2 to the power h, right? So the maximum node can be 2 to the power h plus 1 minus 1, and the minimum nodes can be 2 to the power h. So this is the important condition of total number of nodes, right? What will be the condition for the total number of leaf nodes? So we have mentioned over here, right? So you need not to memorize this stuff, just you need to understand that how we are able to derive it, right? What are things we are using in it, that will be sufficient, right? Total number of leaf nodes here, right? So what are the total number of leaf nodes that are involved here? So as we can see that a certain level have 2 to the power h nodes, right? 2 to the power h nodes, a certain level have it, right? So what can be the total number of leaf nodes? So the leaf nodes are the nodes which are present with the last level, right, which do not have their childs, that are leaf nodes, right? So we need to calculate that what can be the total number of leaf nodes at that particular h position, right? So if we look at here total number of in the total number of leaf nodes, so it can range up to 2 to the power h minus 1 till 2 to the power h minus 1 separately, right? So this is in the power and this is in the, you know, subtracting 1 from this whole output of 2 to the power h, right? So hope you are clear with that. So how we are able to derive this, that these are the leaf nodes, right? Okay, so let's start with it. So the case in which we have a height h, right? So what we can have a single node, this single node, let's say that these two nodes are not there, 5 and 6 are not there, we have a single node, correct? We have that particular single node. So the total number of nodes present at this h minus 1 height will be also a part of the leaf nodes. Why? Because these nodes are not here. That means that this node will also be a leaf node. That means that only, right? If all the nodes are filled at h minus 1 height and these nodes are not there, right? So the upper nodes will be included in the leaf nodes, right? So similarly this tree, if I'll draw it, it will be like 1, 2, here 4 and here 3, right? So this will also be considered as leaf node. Now it is not a leaf node. Why? Because we have 6 over here. But if 6 was not there, that means that we'll include these as a leaf node. Ultimately this one will be counted by this 4, right? So if we have a single node at this particular level, then all the nodes present at this level will be a part of leaf node, plus including that node, that this 4 one, right? And excluding this particular part, right? Excluding this particular 2 node. So ultimately what will happen, that 2 to the power h minus 1 minus this node, that is 2, plus this 4 node 1 will be the total number of leaf nodes if we have this only single node. This is the worst case, right? Because we know that we have a tree of height h, we have a complete binary tree of height h. This is the least possible case we are considering. So these are the total number of leaf nodes, that will be equal to 2 to the power h minus 1, right? And what will be the case? What will be the case where we have all the nodes fulfilled in the last level, right? So that would suffice to a particular perfect binary tree. Perfect binary tree means that we have all the nodes. We have all the nodes, and each of the node has two childs, except the last level, obviously, because that is the leaf node. Except that all the nodes have two childs. That will suffice to a perfect binary tree. We'll get into the discussion on that as well. But here, at the last level, what are the number of nodes that we have? That is 2 to the power h minus 1, because we are taking it as a complete binary tree. That means there is some of the nodes which are pending. Some of the nodes which are pending. If we take complete binary tree in as a perfect binary tree as well, right? So we can say that 2 to the power h will be the nodes at the last level. But if we want to have certain differences between a perfect binary tree and a complete binary tree, that we can say that it can be 2 to the power h minus 1 at the last level. 2 to the power h minus 1 at the last level. This is the particular case where we can see, right? So this is level 2. So 2 to the power 2 minus 1, that is a 4 minus 1, which is equal to 3, right? This is a 3 nodes at the last level, right? So hope we are clear with this, that how we are calculating total leaf nodes, how we are calculating total nodes in a complete binary tree. Certain rules which are associated with this, we have discussed it, but let's one more time clear it out. Okay, so let's clear the space out here. So what are these things? When we insert a particular node in a binary tree, then what points we should be clear of while insertion is that nodes are inserted level by level. It cannot be that you are inserting a node at level 1 and then before filling the complete level 1 you move out to level 2 and then start filling the nodes. It cannot be that case, right? We need to complete one level and then move on to the next level. This is the first case. And the second important thing is we fill left subtree first, right? So left part is filled first, then we'll move to the right part. First left part will fill and then we'll move to the right part, right? So this is the important conditions of a complete binary tree. So this is more or less the whole thing which is required to understand a complete binary tree. Now let's quickly understand what are the perfect binary trees and get some knowledge for that as well. Okay guys, so now let us quickly discuss both the trees, that is a perfect binary tree as well as a full binary tree, right? So before moving to perfect binary tree, let's start a discussion on full binary tree, right? So what is a full binary tree? Let's go with the definition first. A full binary tree or a proper binary tree has either 0 or 2 child for a particular node, right? So if we are considering a one node, then it will have either 2 or 0 child. So let's take this example. So here in this case, how many nodes do we have for this one? That is 2, right? How many nodes we have for this node 2? That is 4 and 5, that is 2. How many nodes do we have for this 3? Is 0, right? So all the nodes, right? These 4 and 5 also are the leaf nodes since they have 0 childs. So all the nodes have 0 or either 2 childs, right? So this is what makes a full binary tree, right? So now if we see, right, we have seen the complete binary tree, right? Now if we want to calculate the total number of nodes here, that will lie into the range of 2 to the power h plus 1 or 2 to the power h plus 1 minus 1, right? So why this? How can we come to the conclusion, right? So at the worst case, what will be the structure of the tree, right? Like if we are considering the minimum number of nodes, right? So for a height h, for a tree of height h, all the nodes will have, all the levels of a tree will have a single node that will have 2 childs. That can be the possible case, because we know that we have a tree of height h, we have a full binary tree of height h. So what will be the case in which at each level we can have the minimum nodes, right? So each child, only one child in a level have 2 nodes, that is 4 and 5. Let's take one more level, that is 6 and 7. So this will be the minimum possible case, right? Because we know that we need to consider a tree of height h, and how we can minimize the number of nodes at each level is, since each a node can have either 2 childs or 0 child. So if we take 0 childs at all the level, that means it will not increment the height. So we need to have a single node which will have 2 childs, right? So we'll take all the leftmost possible nodes with 2 childs. That will be the minimum possible case here, right? And what will be the number of nodes here? Each level will have 2 nodes, right? And this single root will have only 1 node, right? So if we are considering a tree of height, let's say 3, so this is the possible case. And how many nodes we have? That is 2, 2, 2 at all the levels, 1, 2, 3, and 1 node at the root. So that means 2 into height is 3 and 3 levels, right? So 2 into 3 plus 1, which is at the root. So 2h plus 1 becomes the generic formula for a tree of height h to be having the minimum number of nodes as possible. And what will be the maximum number of nodes? Since each node can have 2 childs, right, at max. So we'll consider all the nodes present at a single level will have 2 childs, right? This also have 2 childs and this also have 2 childs. So in that particular case, we have seen in the complete binary tree that what will be the maximum possible case, that is 2 to the power h plus 1 minus 1 by the geometric series formula. That is the maximum number of nodes possible here. So we have come into the conclusion of the full binary tree, that is the total number of nodes will be ranging from 2h plus 1 till 2 to the power h plus 1 minus 1, right? Now let's move on to the perfect binary tree, right? So what is a perfect binary tree? It is the combination of both full binary tree and complete binary tree, right? So that means that at all levels it is filling up the nodes, completely filling up the nodes, and each level, each node will have 2 childs. Each nodes will have 2 child, and that sums up that at last level also we'll have all the nodes, right? So that means that total number of nodes that we have is 2 to the power h plus 1 minus 1. This is fixed, right? It will not lie on the range. It is fixed that each and every node have 2 childs, and till the last level we have the complete structure. We have all the nodes, right? So that means that we have 2 to the power h plus 1 minus 1 at the total number of nodes possible in this tree. So this is the typical example of it. You can see that each node have 2 childs here, except the last level, because the last level is the leaf. These are the leaves that will have 0 nodes, but till this level we have all the nodes completed. We do not have any nodes pending or something like that, right? So this is a combination of complete plus full binary tree. So that's all. We have seen the different binary trees, that what are the categories of binary trees. We have understood the definitions, seen some formulas, and we need not to memorize it. We just have to understand what is the structure and how they are forming it up, right? So that's all from the binary tree.